Today we're going to talk about the work energy theorem. If you remember when we started this unit, we talked about the idea that work can either add or remove energy from a system. And that's the key idea in this case. Again, energy is never created or destroyed, but it can be transferred from one system to another. So we can add energy from one system by, removing it from another system. Work is the thing that transfers that energy. And a quick reminder, work is defined as force times displacement, both vectors, times the cosine of the angle between them. And again, depending on what the angle is, you can either have, if the angle is 0, it can be positive work. If the angle is 90 or 270, it's going to do 0 work. And if it's 180, you end up doing, or in that area, you're going to end up doing negative work, or other angles in between here. If it's positive work, you're going to be adding energy to the system, and so the final energy will be larger. If it's doing negative work, the final energy is going to be smaller than the initial energy. So let's take a look at a couple of examples. In example 1, we've got a 1,000-kilogram car at the top of a 5-meter hill. 2 questions: what's the car's initial energy? If there's no friction, what will be the velocity of the car at the bottom of the hill? So here's our energy work theorem. And the first question is, what's the initial energy? Well, you can probably quickly figure out, in this case, the initial velocity is 0, apparently. And so the only energy it has at the top of this hill is gravitational potential energy. Mass times gravity times the height. In this case, 5 meters. We'll probably put h equals 0 down here for this problem to make our life easier. Plus any work that's being done. So work I'm going to define as any external forces acting on the system besides gravity or springs. There is no friction according to this statement down below here. So we're going to assume that no energy is entering or exiting our system. What's the final energy of the car when it gets down to the bottom of the hill? Well, at that point, it's just going to be moving very, very quickly. And again, remember, the energy of movement is called kinetic energy. And the equation for kinetic energy is going to be 1/2 mv squared. So what's the car's initial energy? Well, just go ahead and solving for the gravitational potential energy, or GPE. Plugging in the mass, 1,000, times gravity will make it 10, times the height, 5 meters, we'll find the initial gravitational potential energy is 50,000, and again, the unit for energy is joules. Now part B, if there's no friction, what will be the velocity of the car at the bottom of the hill? Well, again, our initial energy is 50,000 from just up above here. The work done is 0. And the final energy is all going to be in the form of kinetic energy. No more gravitational because we're back down to h equals 0. Solving this one, plugging in our numbers. 1/2 times 1,000, 500. Dividing both sides by 500, we get 100 equals v squared. Or you can probably very easily see the velocity of the car at the bottom of the hill is going to be 10 meters per second. All of that initial energy is going to get converted into kinetic energy. How about problem B? Well, problem B, very, very similar, except now the car has an initial velocity when it's at the top of the hill. How does that change everything? Well, now my initial energy is going to be both gravitational potential energy and kinetic energy. And I'm going to call it V0 or VO squared, V initial squared, because we'll have a different velocity when it gets down to the bottom. Plus work, again, there's no friction involved, so the work in this case still should be 0. And my final energy at the bottom of the hill, again, if I define h equals 0 right here, it'll have no gravitational potential energy when it gets to the bottom, but it will have quite a bit of kinetic energy. In fact, all of it will be in the form of kinetic energy with some final velocity. So car's initial energy, a little bit more interesting this time. Yeah, it still has the same exact gravitational potential energy it had in the previous problem, but now it also has kinetic energy. 1/2 mass times its velocity squared is also 50,000. So what's the total energy when we get started? Well, it's the sum of these two quantities, which is going to be a total of 100,000 joules to get started. And now solving this next part. So we know the initial energy now is 100,000 from the previous question. There's no work done. So this quantity right here is our 100,000. I should write that out. And our final energy is just going to be kinetic energy, 1/2 mv squared, where the v here is our final velocity. Plugging in our numbers, you'll discover that we get 500. Dividing both sides by 500, we end up with 200 is equal to v final squared. Taking the square root of both sides, our final velocity at the bottom is larger than before. Not by 10, though, it's interesting, but just additional 4.1 meters per second for a total velocity of about 14.1. You're right, okay, we've done a bunch of problems now where there hasn't been any friction. Let's add some friction for this next problem. So what's happening in this problem? Well, as the cart is going down the hill, there is a force of friction acting against it at each and every moment. And again, quick reminder, friction is always acting against the motion or potential motion. So even as it's going down, we'll have this force of 100 newtons, must be kinetic friction, acting this way. As the car is moving down, and I'm not going to show the velocity, as it's displaced this direction. That's our delta x. And just real quick on this one, just so you can sort of think about it and visualize it. What's the angle between the force and the displacement? Well, you should recognize that theta here is going to be 180 degrees, which is going to affect our answer a bit. So, initial energy, again, both of those. This time, there is work being done. There is an external force, a frictional force, times the displacement, times the cosine of angle, theta, and our final energy is just going to be kinetic. Car's initial energy, in this case, plugging in our 180 degrees that we just found, our displacement, which is the length of the track, 15 meters, and the force, which is 100 newtons. Probably could have color-coded that better. Car's initial energy is going to be the exact same as before, 100,000 joules. But now it gets a little bit more interesting. If you work this out, 100 times 15, cosine of 180 is -1. So this is going to be -1,500 joules. That's the amount of energy that is going to be removed from my system. And if you're curious, it's going to probably end up in the form of heat, or E dis. Solving this, subtracting the 1,500 from the 100,000 gives us that. Dividing both sides now by 500, you get 197 is equal to V final squared, or V final now is about 14.0 meters per second. Just slightly less than it was before in the previous problem where there was no friction. This next problem, and again, my apologies, I got B marked off here. This time the car is going to start out with the same initial energy. It's going to have no friction this time, so no work being done. But the final energy this time, it's going to hit a spring at the bottom of the hill and compress it. So we're going to end up with the elastic potential energy, EPE. Car's initial energy, exactly the same as it's been in the previous problems, 100,000 joules. But the difference in this case is the initial energy plus the work done, 0, is going to equal elastic potential energy at the bottom. We're given the spring constant is 10 to the 5th. And so if we plug that in, you get, and then multiply both sides by 2, 200,000 divided by 10 to the 5th gives us just 2. 2 is equal to x squared, or x is equal to the square root of 2, or 1.41 meters. Again, if you can just figure out what types of initial energy you have, if there's any work being done, and the final types of energy, you can solve this. This one's a little bit more interesting. I didn't actually give you a drawing in this case. What do we have in this case? Well, we've got a car that's initially at rest, and then we're going to have a person pushing on it who's going to try to get this thing moving by pushing as hard as he can. What direction is his force going to be? Well, he's going to be applying a force in this direction. And according to the document, I'm reading part B already, that's going to be 1,000 newtons. But there's an additional force going on here. There is a force of friction acting against that motion. Now it's smaller, so the car is still going to gain speed, but we've got 500 newtons acting against that motion. Finally, we're told that the person's going to push the car for a total displacement of 5 meters. So delta x here is going to be 5 meters. And solving this one. First question, what's the initial energy of the car? Well, if you think about it, the car starts from rest. So it has no kinetic energy. It's on level ground. I guess we're going to assume that we're going to define that as h equals 0. So it has no gravitational, it has no elastic. The total energy in this case is just 0. Now the work being done is both the work being done by the person and the work being done by friction. So the total work in this case is the sum of both of those. And our final energy is going to be kinetic again. So initial energy of the car, 0. That's easy. And now trying to solve the second part. Putting in all our numbers, we've got an equation from above. Putting in the numbers, the amount of work that the person does is 1,000 joules times 5 meters times the cosine of 0 degrees. Why? The angle between these two things here is 0. Meanwhile, the work, or the angle between the displacement and the force of friction, is actually 180 degrees because they're acting opposite. Displacement is towards the right, force of friction towards the left, so we end up with 180 degrees for that. And final kinetic energy, 1/2 mv squared. Plugging in the numbers, the work done is 500 joules. The work done by friction, negative 2,500 joules, equals the kinetic energy. Or we end up with 2,500 equals the kinetic energy. Multiplying through by that 1/2, we get 2,500 equals 500 times v squared. Or v squared is equal to 5 if we divide both sides by 500, giving us our final velocity about 2.24 meters per second. Now, we've been talking about the fact that you can actually set the 0 point for gravitational potential energy anywhere convenient. And you might say, wait, does it actually work, or does it work as well as we think? Well, in this case, we've got a ball, or a lead ball. It's 1 kilogram. Its initial velocity is 0, and it's being held right above this well that's 10 meters deep. My question is, what's the gravitational energy, or potential energy, and the kinetic energy initially? Well, in this case, it's pretty easy. Since the height is 0, it's 0. Kinetic energy is 0 because it's not moving. Just before it hits the bottom of the well, its gravitational potential energy is going to be negative 100. And if you don't see that real quick, the height at this point is going to be negative 10 meters. 10 meters below where it started. And I think we talked about the fact that gravitational potential energy can be negative. And so in this case, that. What's its kinetic energy? Well, we know that energy must be consumed. And in this case, if we assume that the work done by friction is 0, the initial energy has to equal the final energy. The total energy beforehand is 0. So the total energy at the end, if there's nothing adding or removing it, also has to be 0 joules. What's the kinetic energy then? Gotta be? It's got to be positive 100. So the sum of those still gives us 0. It's an interesting thing. You can also work out the math. If you worked it out, how fast something would be going, if it fell due to gravity for 10 meters, you would discover it would have that much kinetic energy. But let's just go with this for a second. So what am I aiming at with this problem? Well, what happens if we set h equals 0 at the bottom? Well, now we have a different situation. Now the height up here is 10 meters. So what's our gravitational potential energy now? Well, it's mgh. In this case, m is 1, gravity is 10, height is 10 meters. So gravitational potential is going to be 100 joules initially. And the initial kinetic energy is still that. Gravitational energy at the end is going to be 0 because now I'm down to h equals 0 down here. But again, energy must be conserved. Total energy beforehand was 100 joules. It's got to be 100 joules down below. But if gravitational potential energy is 0, the kinetic energy then has got to be, if you can't see it already, 100 joules. Finally, what if you just throw it in an arbitrary spot? This gets a little bit strange. Just go with me for a second. What if I set h equals 0 right in the middle of the well? Well, that would mean the height at the top of the well would be 5 meters. And the height at the bottom of the hill, or bottom of the well, sorry, would be negative 5 meters. What does that do to our work? Well, it gets a little more interesting. Now, gravitational potential energy, mgh, is going to be equal to 50 at top. Kinetic energy is still 0. But at the bottom now, the height is negative 5. If you plug in mgh, 1 times 10 times negative 5, you'll discover that's negative 50. But again, our same rule has to apply. Total energy beforehand was 50. What does it have to be at the bottom if there's no friction? It's got to be 50 as well. But wait a second. How could this add up to 50 if the gravitational potential is negative 50? The answer is, well, kinetic energy then has got to be 100. Notice that no matter how we set this, the kinetic energy at the bottom is always 100, no matter what we do. Finally, a couple of quick ones on this one. The energy flow diagrams. Energy flow diagrams is sort of using this whole idea of the initial energy. In this case, the initial energy is going to be represented by a series of bar graphs. And the final energy is going to be represented by these bar graphs down over here. And I'll show you what I mean real quick. And the work in this case is going to be represented by this energy flow diagram. This represents how much energy is going in or out of our system due to the work. So let me show you how this works. We've got a bullet. It's going to run into a wooden block that's sitting on a frictionless surface connected by a spring. The bullet's going to embed inside the block, and eventually both the block and the bullet are going to move over, and forgive me for drawing on top of this, until the spring gets super compressed and the block briefly stops. The interesting thing about this problem is defining your system changes your answer completely. So for this particular situation, we're only going to look at the bullet. Now, what kind of energy does the bullet have initially? Well, before I answer that, let's just assume that the bullet's at h equals 0. Remember, you can set it anywhere you want. We just kind of showed that. This makes our problem a little bit easier. So then if h is 0 there, it has no gravitational potential energy. Bullets don't have any elastic potential energy, but it does have kinetic energy. And this is a qualitative graph. I'm just going to arbitrarily give it 4 units of energy, kinetic energy. What kind of energy will the bullet have over here? Well, this gets a little more interesting. The bullet stops, so it has no kinetic energy. It has no gravitational because it's still at the same height. A lot of students think, oh, it's got elastic potential energy. Yeah, the spring does, but remember our system is only the bullet. Does the bullet have elastic potential energy? The answer is no. What's the one thing the bullet might have? Well, it probably warms up. In fact, I guarantee it warms up. It warms up and the block that it embeds warms up as well. And so what's going to happen here? The only type of energy the bullet's going to have at the end is E-dis, heat. And not all 4 units of its initial kinetic energy is going to go into heating up the bullet. Some of that energy goes into heating up the block, and some of that energy goes into compressing the spring. Again, the exact amount here is completely arbitrary. I'm going to guess about 1 unit. About 1/4 of it goes there. What's the energy flow diagram going to look like? Well, we started out with 4 units of energy over here. We end up with only 1 unit here. 4 units initial, 1 unit here. What must the work have been? Well, the work must have been -3. In other words, 3 units of energy must have left my system. How do I represent that? In this case, just with an arrow. And the arrow here does not represent force. Normally I do fat arrows as that. But in this case, it represents the work or the energy leaving my system. 3 units left. Start out with 4, ended up with 1. So we're going to do the same problem, but this time I'm going to change the system to the block. And I'm going to put h equals 0 now on the tabletop. What kind of energy does the block have initially? Does it have kinetic? Nope, it's stationary. Does it have gravitational? Nope, it's sitting at h equals 0. Does it have elastic potential energy? Nope, it has no initial energy. However, at the end, what does it have? And I don't want to redraw it again, but if you remember, it stops briefly, so it has no kinetic, it has no gravitational, and it has no elastic, because all the elastic potential energy is stored in the compressed spring. What does it have? It does have a little bit, it gets warmed up. Remember I told you as a bullet runs into it, it heats up. In this case, my initial energy was 0. My final energy is 1. I have 1 unit drawn over there. Again, just an arbitrary choice. In this case, what must be the work being done? Well, in this case, work must have done positive 1 unit of work. In other words, 1 unit must have entered my system. Work must have been positive because my final energy is greater than my initial energy. The angle you put the work in is completely arbitrary. You can point it in this way, you can point it in this way, anywhere you want, just showing that energy entered my system, which is represented by the circle down below. All right, what if we change it again? What if our systems are spring? You're like, okay, get it. In this case, the spring is not moving, so it has no kinetic. It has no gravitational. I'm going to set h equals 0 right there again at the bullet. It has no elastic potential because it's not stretched or compressed or anything at this point before the bullet does anything. At the end, what's going to happen? It's going to be compressed. If you remember my original diagram, I drew it really super compressed. And I'm going to say 2 units went into it. Again, a completely arbitrary choice, but as you might see, a kind of requirement based on my other 2 answers. You'll see why in just a second. All the rest of the energy went into heating up the bullet and the block. What's my energy flow diagram? I start out with 0 units over here, 2 units over here. What must have happened? 2 units of work, sorry, I got cut off. 2 units of work must have entered my system. Because I end up with more energy at the end than I started. Finally, what if I define everything as my system? This gets much more interesting, and now you'll sort of see the overall thing. The bullet is now part of the system, so yeah, we've got 4 units of kinetic. Again, the choice of 4 arbitrary. What's my final energy going to be? Well, it includes the spring, so I'll have those 2 units, and it also includes the bullet and the block. So beforehand, we had 1 unit for the bullet, 1 unit for the block. Now my total energy dissipated is going to be 2 units. What's my total energy beforehand? Well, 4. Over here, it's 2 plus 2, which is still 4. How much energy entered or exited my system? The answer is none at all. So in this case, there's no arrow going in or out of my system. The total work entering or energy entering or exiting my system, the work is 0. Finally, the last thing I want to talk about is you'll hear this term mentioned, mechanical energy. Mechanical energy is the sum of the system's kinetic and potential energy. And when we talk about potential energy, it's both gravitational potential energy and elastic potential energy. So in most systems, the mechanical energy is conserved unless there's E disgenerated. Good luck. You should be able to do most of the worksheet tonight without any difficulties. Good luck. Work together. Have fun with it. Talk to you soon.